Thank you very much. I'd like to thank Tom for inviting me to visit the Institute and to have this opportunity to speak. So I'll be talking about work that I've been doing for the past few years. So let me start. Okay. Yeah. Okay. So in this talk, I'll be considering specifically, I'll be considering nonlinear PDEs, but specifically, for example, the nonlinear Schrodinger equation, which I suppose most of the people in the audience know, maybe except one, maybe you also know, Laurent, and the nonlinear wave equations. Okay, so I just added these higher order terms, just show that the method is general, but for the sake of the talk, you could just forget about this. Okay. And so these exponents P, they are arbitrary.
The first equation you have there looks like you got a focusing one.
I'm looking for small solutions.
So you don't care?
Yeah. Unfortunately, I do not need to care about this. Okay. So I'll be observation theory, actually. Now, without the nonlinear term, we have the linear Schrodinger equation. Okay, so it's just a time evolution of the Laplacian. It describes the motion of a free quantum particle, as I think most of us know. The nonlinear terms in nonlinear Schrodinger approximate the many-body interactions. This is what we learn in physics in any case. And similarly, the nonlinear wave equation, it's also called nonlinear Klein-Gordon equation, which I'll explain in this case. It describes the relativistic motion of a particle, taking into account also the effect of many-body interactions. Okay, so this is, and they are among the most important and most basic equations coming from physics. So this is why we are studying this, one of the reasons. And the dynamics of the linear Schrodinger and wave equations are completely described by the corresponding eigenfunctions and eigenvalues. Because these are linear equations. And the eigenfunctions form a spanning set, and all solutions are their linear superpositions. In the presence of the nonlinear term, there is no longer this linear superposition because it's a nonlinear equation. And simplest generalizations of eigenfunctions are the time periodic solutions to the nonlinear equations, right? Are you familiar with this? Okay. The next generalizations on the ladder are the quasi-periodic solutions. It just means that they're periodic with several frequencies, right? You have a linear superposition of periodic frequencies, periodic solutions. So I give an example. For example, when alpha is irrational, this simple function is quasi-periodic in time with two frequencies, 1 and alpha, right? Okay, so it's a simple example of a quasi-periodic function. Now, quasi-periodic solutions can be seen as bifurcations of linear superpositions of eigenfunctions, right? This is a simple-minded way of saying this. So if there is only one eigenfunction, then bifurcation leads to periodic solutions. Okay? As mentioned earlier, they are hence quite natural. So I'm just convincing you what I'm studying seems to be a natural question. Okay? Clearly, I suppose perhaps you all agree that not all linear solutions will bifurcate to nonlinear solutions. Okay, you add the nonlinear term, not all the linear solutions will continue. Yeah, it's reasonable. So, therefore, one of our tasks is to impose reasonable conditions on the linear solutions, right? Which are often algebral, geometric, and arithmetic, as we shall explain. Okay? Yes?
So, are you talking about periodic or small decay solutions?
I'm talking about spatially periodic solutions.
Oh, okay. So you're talking about
on the torus, yeah. Yes. So what I want to say, a priori, you need to impose some geometric conditions and sometimes also arithmetic conditions on the linear solutions themselves in order to be able to continue them. It's a priori necessary, I think, so that they could become solutions to the nonlinear equations after small deformation, right? This algebraic aspect could also be understood from a variational point of view, and more on this later if I can go into this just a bit, okay? So now there are some technical points which have receded to gray, so I think I'll skip it right now, okay? We can come back to it. Now, generally speaking, in order to have solutions which are quasi-periodic, the equations need to be posed on a compact manifold. This is anticipating. And the most basic is perhaps the flat torus TD, which leads to time quasi-periodic but space periodic solutions, right? You can lift the torus to periodic RD. Okay? So this is our setting. And the plan of the talk is to give an idea. Okay, so I can only give an idea, give some indications of the proof of the following. Now we have a theorem. You can put it in a much more technical, precise way, but I prefer not to do it. Okay. So I just write one sentence. There is a class of global solutions to the nonlinear Schrodinger and nonlinear wave in arbitrary dimension D. Okay, I think this is a fairly big key point, that it works in any dimension. And for arbitrary nonlinearity P, these are quasi-periodic solutions in time, yeah, which are Gevrey functions in space and time. Okay, Gevrey functions are something rather technical. They are C-infinity functions with control over the derivatives, so they are just a bit worse than analytic. Okay, it's a technical thing. Okay, so this is what we can do. So this is the result, but perhaps equally important is the following points. Along the proof, we establish a new method, which is based on Anderson localization. So that by that I mean the multiscale analysis of Fröhlich and Spencer, harmonic analysis, so it's the work of Bourgain, Goldstein, Schlag, and algebraic analysis. So that's my little contribution. So there are 3 components. So let me just explain a bit the 3 ingredients, okay, the role they play here. So Anderson localization, this is the basic mechanism underlining this line of research. So everything this is the basic mechanism. And so the use of harmonic analysis is when you have 2 eigenvalues which are very close. Okay, you use harmonic analysis to control the small divisors, right? As I explained, we are perturbing away from the linear equations, so obviously eigenvalues will play an essential role. Okay, so the harmonic analysis I use to control when the 2 eigenvalues become very close. Okay? And now the algebraic part is to control the geometry when the 2 eigenvalues are equal. Okay? So this is the geometric part.
That's how you deal with high multiplicity?
Yeah. Yeah. That's the geometric part. So the first 2 ingredients are so the third part is a bit different from the first 2. Okay, this is the geometric step. Okay. Now, these quasi-periodic solutions are also called KM solutions after Kolmogorov, Arnold, Moser. They are also called tori. KM solutions are generally obtained using the Hamiltonian formalism. right? That was how the celebrated theorem was proven, i.e. in phase space, right? You have the point in space and the velocity, okay? While our multi-scale method fits naturally in the Lagrangian formalism, i.e. in the configuration space, okay? If you like, it's on the base manifold. The realization only came very recently, the two different points of view. And for example, nonlinear Schrodinger is first order in time, right? And naturally in the Hamiltonian formalism, right? You have the velocity. While nonlinear wave, second order, and naturally Lagrangian, right? The Lagrangian equations of motion are second order in time, or Newton's equation, F equals to ma. And of course, nonlinear wave equation also has a Hamiltonian representation as a system of first order equations with u and u dot as conjugate variables, right? This we all know from, maybe first year college. But there is an analysis subtlety involved. And it's kind of surprising, this analysis subtlety up posteriori very obvious, but it's not so well known. Okay, so I'll come back to this analysis point. Right. So here I want to give some historical note. So some historical context. After the success of KM theory, Moser of the Kolmogorov, Arno Moser, proposed to construct quasi-periodic solutions in the Lagrangian formalism for geometric reasons. Okay. This is natural as the another reason, analysis reason. We can see, another if you agree, that the Lagrangian formulation could be more general. Okay. For example, it requires less smoothness, right? It's a functional, and deals more naturally with higher order equations. Yeah?
Just to clarify language, when you talk about Lagrangian formalism, you mean let's work with Euler-Lagrange equations, second order? How do you do you say without the Legendre transform?
No, I just mean I work. So I'm taking the specific example of nonlinear wave equation. It's a second order in time. I term this.
Do not mean a variational calculus looking for critical point.
This might be the next step of trying to understand. It has to do with what I do is not variational at all at this point. But perhaps if you want to take that point of view, you can understand some of the algebraic aspect, actually. Okay. I'm just trying to understand what I'm doing, but this is later. Oh, I'm saying that right now, I just take the second order equation, I deal with it directly. I do not transform it into a system of first order equations.
Do you think there could be a connection with, if you start working variationally, you get into Aubry matter theory, which is also variational, right? Could there be a connection?
Yes.
So you get into a node diffusion issue.
Well, I think these are all the things that's now lurking in the background. Okay? It's all recent, all this understanding. Okay? The fact that you stay with the more primitive formulation, so to speak, F equals to ma. Okay? All right? At this stage, I do not write a second order equation into a system of first orders. That's all I mean. Okay, so here maybe it's partial answer to what you were saying. Based on Moser's notes, so Moser wrote some notes. Salomon and Zander, maybe you have at ETH, they show the existence of quasi-periodic solutions using the Lagrangian formalism.
So quasi-periodic solutions to what?
To a finite dimensional system. Then I re-looked at that paper. They started with the Hamiltonian equation, and they actually did a Legendre transform and work with the second order equation. Okay, and for me, I have a nonlinear wave equation, which is second order to begin with. Okay? And I think they might have done something more geometric when you have this, the working with the functional, but I don't know. So the main point, as we know in this business, is to overcome small divisors, right, in order to obtain an implicit function theorem. Okay, so that's the work of Salomon Zander, but this is in finite dimensions. Okay, so they transformed the first order to second order, and they dealt with that. And our theorem deals with PDEs, right? The theorem I quoted, and it's therefore in infinite dimensions. Okay? The proof uses multiscale analysis. Multiscale analysis is Anderson localization and vice versa to control small divisors. Okay? Now the torus setting, the spatially periodic setting. Coming back to the problem at hand, we start from the linear equation posed on the torus, right? This one and this one. Okay? Now, where the term 1 is added in order to avoid the singularity at 0, because what you're interested in, you're taking the square root of the Laplacian, and if you don't have 1, you have a singularity, so you see it, the bad effect of singularity. Here, this is avoided, and it is usually called the mass. And when you add the mass 1, it's called also called nonlinear Klein-Gordon equations. So we avoid the singularity. Now, these linear equations are solved using Fourier series, right? And spectral theory. The spectrum of the Laplacian is this, except these are integers. Okay, so it's a sum of square of integers, while that of the wave operator is this, which is just taking the square root. Okay. Now, they play an essential role in our analysis, right? Again, because we perturb from a linear problem. We know that in dimension 2 and above, they are highly degenerate, right? The spectrum of the wave operator D is moreover dense, okay? So let me, it just means, what I mean that the eigenvalue spacing goes to 0, okay? Which makes NLW even more difficult. It's degenerate and dense, okay? It sounds horrible, right? Okay, so I said I have a result for both nonlinear Schrodinger and nonlinear wave, but I'm going to explain our method using nonlinear wave as for two reasons. Well, first reason, it is more difficult. But there's another reason, maybe even more important, is that it also represents a generic case. Okay? In the following sense, according to the theorem of Doistermatt and Gilliman, the spectrum of the differences of eigenvalues of a first-order elliptic operator on a generic compact manifold is dense. Okay? There's a very nice survey paper by Gilliman in Duke Journal of Math on this aspect. It's very striking. So therefore, we take the nonlinear wave on the torus because it's dense, right? Generic. Not. But anyway, it can represent the generic case. Yeah, that's one of the other reasons. And since we seek real solutions, okay, this is classical mechanics, we use cosine series. I do not want to see I in this business. And for nonlinear Schrodinger, we look for complex solutions and Fourier series. Okay? Now, the space-time cosine series. The linear equation admits solutions of the form. You agree with me, yeah? Should I, yeah? More generally, let U0 be a solution of finite number of frequencies, so you take a finite linear combination of this. Okay? I'm sorry, the notations are perhaps a bit heavy, okay, with sub-indices and super-indices, but so
your JK is what, a K vector?
I'll go to the next slide. So I have to illustrate the notation, right? It's a bit heavy, I'm sorry, but okay. So let us fix d equals to 3. We work in 3 dimensions, and we take b equals to 4 frequencies in time. Okay? And then there are 4 vectors in Z3, right? The Fourier duo of the 3 torus. So I just arbitrarily took example. J1 is 1, 2, 3. J2 is 5, 6, 7. J3 is this. And J4 is this. Okay? Which are the vector space frequencies. Okay? And the 4 scalar time frequencies, so I compute this. They have square roots coming in now. Okay? Which are sometimes written in the vector notation omega, which stands for omega 1, omega 2, omega 3, omega 4. Okay? So let me just predict or say things that, as you see, not all these frequencies are good. So this is where some number theoretical consideration will come in. Okay?
What do you mean they're not good?
I'll explain. A good mean you can continue the solution. Okay. Okay. Good. Square roots come in, so that you need some arithmetic conditions.
So can we see the previous equation again?
Yeah.
Now that they know what JK are, can I see the previous equation?
Oh, yeah. That's a good idea. So,
Thank you.
so k is 1, 2, 3, 4. Okay. I apologize. I cannot find a better ways of writing this.
Yeah, so I'm so confused.
Yeah.
J, K.
Yeah, I know what
no,
I know that the
JK is
problem. This J is generic. This is specific. This is.
It's not a number, it's
It's
a vector.
a
And
vec-
JK squared means Euclidean length.
Oh yeah.
Okay.
Yeah. Sorry.
So
JK
that's
square.
what I'm
Oh,
trying to
okay. Yes. Okay. So. Yeah. Yes. So, J square stands for. Oh, no, it's bad. J dot J. Yeah. Thank you. Yeah.
And the K means?
K is the index from 1 to B. On the next slide, there are 4.
Okay.
Yes. Okay.
So you're looking for a quasi-periodic, you're going to be looking for a quasi-periodic solution with 4,
Yeah.
with B, but in the example you gave,
4. Exactly.
4 Fourier frequencies.
That's right,
4
yeah.
irrational frequencies.
That's right. Okay. Yeah. Okay. Is that clearer? Okay. So note at this stage that the frequencies omega equals to omega 0 are fixed, right? These are frequencies, the linear equation, so they're independent of the amplitude. So, time quasi-periodic solutions may be viewed as periodic on higher dimensional torus, right? To each frequency, we add a dimension, so as an ansatz, we seek solutions of this form. Okay?
But that's confusing. So your omega is actually a function of J, has to be, no? Or not?
Omega is a function of jk, actually.
Yeah, so omega in this sum,
Yeah.
does omega depend on the index J or not?
It depends on index j sub k.
J sub K.
Yeah, it doesn't. I mean, this j is generic.
Yeah.
You know, we have to rewrite jk slightly differently. I think this is where the
The
confusion.
omega, it should have an index, another index.
Yeah. Okay. So I apologize about this. Okay, so I rewrite this. So cosine has this. So what you can see that for cosine, you only just have the base vector for the linear solution. And when for the nonlinear problem, you are going to bring up higher harmonics, which I call n. Essentially, that's what happens. Okay, I really apologize for the notation, but this is the idea. Okay. And I make a remark, the time part of the Fourier series can be understood using the substitution partial t goes to omega partial omega on the torus. It's a standard thing. Okay, now we come to the matrix problem, right? We have Fourier series, so we are you have natural matrix problem coming and the Anderson model. So that's the Anderson localization. Okay. Using the cosine series ansatz, the linear Klein-Gordon equation becomes the diagonal matrix operator, right? Okay. As mentioned earlier, maybe I skipped the slide. Yeah, that's right. Now, for the nonlinear problem, omega is to be determined. Okay, it's going to be modified by the nonlinear term. Yeah. For the linear problem, omega is independent. But okay, so later, omega needs to be determined. Yeah. To leading order, of course, it's the linear frequency. Okay. Since we perturb from the linear solutions U0 as an initial approximation, omega equals to omega superscript 0 are the linear frequencies, right? Okay, in the example, k is 1, 2, 3, 4, okay, of these square roots. So the diagonals can be 0, right? When it's a solution to the linear problem. It's 0 when it solves the linear problem, okay? And the off-diagonal matrix is a convolution matrix, right? Since you have a nonlinear term, after Fourier transform, it becomes a convolution matrix, yeah? So therefore, you have the linear self-adjoint matrix operator, right? This is the diagonal part. And then you have the convolution matrix, where for illustration, I just took the cubic nonlinearity, okay? After you linearized, yeah? You just have this. Okay? This term is just the Fourier transform of U squared. So to illustrate this convolution matrix, this is P. Let us take a simplified example and assume U equals to U0, just cosine x, okay? I mean, our cosine is a bit more complicated, but let's just do this. And since the symbol is U squared, it's cosine squared x, this is the double angle formula, right? It's correct. P has diagonal entry minus a half. This is our diagonal. And two off diagonal entries a half, yeah?
So that last term on the first line up there, that's going to act by a convolution, right?
Yeah, it's a convolution, yeah.
Well, you've written it as a convolution of two things, but it acts also.
Yeah.
You have a star there that says it
that's
acts
right.
by a
I always forget
Otherwise
this
it's
stuff.
not clear.
That's right. I always forget this stuff. I'm so sorry.
It needs to be there.
Okay. Yes.
There's a sign mistake.
Where? Where's the sign?
You are pointing to.
Huh?
If cosinus cos squared.
A plus 1?
1 minus cosinus 2x.
Okay.
Yeah.
Okay. Oh, okay.
Yeah, clearly. And it should be a plus sign.
I made a mistake. Okay.
Plus one.
Okay, I made a mistake. But in any case,
Yeah, no,
okay, it hardly matters what I'm going to say. So, okay, so that's our problem after the linearized problem, okay? And now I claim that it's Anderson model very relevant. So what is the Anderson model? The Anderson models are, on the other hand, as follows. There's the random Anderson model is H equals to V plus Laplacian. So you have the diagonal VI plus Laplacian. Laplacian is a discrete Laplacian. Its symbol is cosine x. So where VI a family of IID random variables. Okay, so you have a matrix on diagonal. You just have random entries. A Laplacian, discrete Laplacian. So this is the model in the 1983 foundational paper of Fröhlich and Spencer for Anderson localization. So that's the random Anderson model. So and then you have a quasi-periodic model where instead of a family of random variables, you put in a quasi-periodic function. So for example, where omega is irrational. For example, in one dimension, you take this, cosine and omega plus theta, right? Okay, which leads to the celebrated almost Matthew operator. It's really a very famous operator. And in 2D, a special case of Anderson, you can also, and omega, you can also do the dynamics in 2D. And in 2D, this is a special case of Anderson localization studied in the seminal paper of Bourgain, Goldstein, and Schlag, Z2. Okay. And also uses Anderson localization method and harmonic analysis. It's not a dynamical system method, right? Okay, so these are the two examples of Anderson models. Okay. Now, let's go back. So these are the Anderson models, and mine model looks like it, right? So this is your discrete Laplacian, if you like. Of the analog discrete Laplacian, and then I have something on diagonal, right?
So when
Yeah.
where does u hat 0 convolve with u hat 0 come from? Where does this come from?
It's the Fourier transform of u square.
Yeah, but you have a different nonlinearity. Where I'm confused.
Yeah.
Oh, you only keep track of the second order correction. So why u squared in your equation?
Oh, yeah. Maybe I skipped something. So I linearized the problem. Yeah, I should. So you have I dt minus Laplacian u plus u cube equals to 0. I'm taking the cubic case. Okay. Yeah, I'm just taking the cubic. I did say right. Where for illustration we have set p equals to 1. P means p equals to the cubic case. Okay.
So then you're going to linearize successively around
Yeah,
the
yeah.
various
Yeah,
solutions,
that's right.
And then each linearization will look something like.
Yes,
will look something like.
that's right.
quasi-periodic,
That's right. But unfortunately, today I might only have time to talk about the first step, first iteration, which is the new part. Afterwards, it's work related to Bourgain, Goldstein, and the Schlag. Okay. Today I can only talk about the geometric part. Okay. So these kind of matrices look alike. Okay, this is what I want to say. Now the H and the T is my linearized operator, they look alike, okay? Particularly the quasi-periodic H, right? I also have n dot omega in the diagonal, except omega is a parameter in H. So the difference between the Anderson model and my model is that the Anderson model, these are parameter, it's a family of operators. It's not a fixed equation. It's not fixed. Mine is fixed. That's the difference. While for me, omega equals to omega is a parameter in H in the previous, all this previous work I cited, the Anderson model, while omega equals to omega 0 is fixed for my problem, for the first step. The parameters will have to come elsewhere, from elsewhere.
The parameters, it's true that your parameter is naturally fixed because that's the free part.
Yeah.
But of course, you have your amplitude, which modifies
Precisely.
the Laplacian. So whether
Precisely.
you fix that or you fix, it's just a matter of scaling.
Well,
I mean, in terms of amplitude. Just a matter of scaling.
before you can use the amplitude, you have to do geometry. This is what I'm saying, because the problem is very, very degenerate. This is why so far there has not been a variational solution. Okay. This is almost the key point. It's a very degenerate
Do you
problem.
understand what I'm saying, right?
Yeah,
I mean,
sure.
Whether you put the
Sure.
coefficient
Sure.
in front of the
Yeah.
Laplacian
Sure.
or in front of the
Yeah. Yeah.
potential makes really no difference.
Okay. But right now it's a geometric problem. I don't have any
Well,
parameter.
You have to explain what the geometric problem is.
That's right. So this is what I'm going to come up to. Okay, a real geometric problem because of the degeneracy. So, but, okay. So at this stage I have no parameters. Things are very degenerate. So what to do? What are you going to do? So, but before doing that, let us present first the Fröhlich-Spencer-Anderson localization scheme for parameter-dependent H. Okay? and then explain the additional algebra geometric step needed to deal with my omega, which is fixed at this point, okay? Which is to leading order fixed. Okay? So this is what I have to do before I can use what you have done. Now, but let's explain, because this is the basic mechanism, okay? Let me explain this multiscale analysis. The scheme invented in Fröhlich-Spencer is a multiscale analysis using appropriate finite sets lambda to approximate ZD, okay? So matrix with index ZD, and consists of 3 steps. Initial scale or initial scales Green's function estimate in a sufficiently large box. Okay, there are always a small perturbation, so it's large, sufficiently large box. Number 2, you cover large boxes by smaller boxes, right? It's very reasonable and geometric, and obtain Green's function estimate for the larger box. Okay, it's a good idea. Yeah, very good idea. Natural. Central is that there are only but a few bad small boxes. You cannot exclude bad boxes, okay? Where the Green's function estimates are not good, but still there exists a priori estimates. They cannot just be bad, arbitrarily bad. They have to be controlled. And in the field of Anderson localization, they are called Wegner estimates. Typically, they come from eigenvalue spacing estimates. Okay, this is necessary. Okay, and it's a very nice picture. You have you cover big boxes by smaller boxes, and you allow some bad guys, but they cannot be too bad. Okay, so this is the idea. And the third part is, I mean, here's because it's a linear problem, you want to talk about the spectrum and use the Green's function estimate to prove that the spectrum is pure point. That's what you mean by Anderson localization. Okay? Okay, so that's a scheme invented by Tom and Jörg, 1983. So the scheme is the underlying scheme for this line of research. Okay? Now, returning to the problem at hand, let's remember that we try to solve some nonlinear equations. So let's return. Okay, so it will be necessary to introduce the concept of the bicharacteristics. Okay, so we return to our geometric problem. In the nonlinear construction to prove the theorem, the key is the invertibility of the truncated linearized operators, that is the Green's function estimates, right? We use it's Newton's scheme, huh? So you do not escape that. So we call the scales, I call the scales in step 2 the asymptotic regions. It's when you start iteration, okay? I call these asymptotic regions. The iterative scheme in the asymptotic regions are the same for my t and h. Okay, the details, of course, but conceptually it's the same. It's the asymptotic. This part is universal. Okay, once you get to that point, it becomes universal in some sense.
What do you mean by universal in this context?
It's the same way of doing things. Well, you know, that's what I mean.
I really don't know what you mean by this second paragraph. I mean,
yeah?
Even I'm not sure what you mean by step 2. I mean, I don't even know what step 1 is. So.
Step 1, the initial estimates.
On what?
Of the Green's function in the finite volume.
Okay.
Because the problem is very degenerate, that's different. And the second part, iteration, is not that different. That's what I want to say.
How do you pick the size of the first scale?
Yeah, all this will come in. Okay? This is what I meant to say, is that once I have the initial step, I can just use what you have, the mechanism you have. Okay? What is new here, what I'm talking about, is first step, because of the degeneracy.
It's slightly confusing that Fröhlich-Spencer should apply, because you said yourself you know the Wegner estimates and separation of eigenvalues.
Yeah, yeah.
But your problem is so highly degenerate. You have, as you said, eigenvalue spacing
Yeah, yeah,
to
yeah.
0,
Yeah.
and you have
Yeah.
increasingly arbitrary high multiplicity of the
Yes, yes. What I mean, the general scheme, what I mean, the general idea remain the same. Not the details. No, no, no. Details are very different. No, no, no. I'm not talking about details. Conceptually, it's the same. This is what I meant. I'm not talking about details. No, no. The details are very different. I cannot enter this, but conceptually, it's this idea. That's all I can say. Is that okay? Yeah.
Fine, but I mean, yeah, it is a very different scheme. I mean,
It's a, yeah, okay. So, okay, so the first step is very different. This is because in T, the diagonals can be 0. Okay. Since there are no parameters at this stage, while using the parameters omega, the diagonals in H can be kept away from 0 by taking away a small setting omega. So, in other words, what I want to say is that the perturbation theory for T is singular. Okay? For example, for the parameter-dependent quasi-periodic Anderson, a singular case would be this. You have a delta in front of the coupling discrete Laplacian, and then you have a delta in front of omega. Okay? So this would be an example of a singular case. So this is what we have to deal with at some initial scale. That's what I mean. Okay, so that is fairly different.
Yeah.
Okay. Generally speaking, in the singular case, the estimates need to be more quantitative. Maybe this is your question. Because of, see, in the regular case, the one I wrote before, there's no delta here, right? Here I have delta on both sides. Okay. For the singular, in our case, analysis alone does not suffice to deal with singular perturbations, okay, because of the degeneracy. And we need to analyze the geometry of the zero set, right? What is bad is when the diagonal is 0, right? Otherwise, there's no problem, okay? We call the above set the bicharacteristics, okay? Why bicharacteristics? Because this factorizes into two terms, yeah? So, okay. And its geometry will play an essential role in estimating T inverse, okay? The geometry of the zero set. And this step is non-perturbative, so there's no perturbation here. So, a separation property on the bicharacteristics. So for H, so if I go back to the Anderson model, the bicharacteristic set C, the corresponding bicharacteristic set C is empty, right? By exigencing omega, because you have a parameter to tune, okay? The diagonal is never 0. This is not possible for T, right? Because, you know, there are solutions to linear equations that you perturb from. The next best thing, well, what can you do? It's not empty. The next best thing is then trying to achieve some separation property, right? Or in other words, some clustering property on C. Okay, so let me draw C. C are the hyperboloids, yeah? So C, so I write J here, and here, C is something like this, right? Okay, they are there. It's not empty. So what you can try to do is derive some separation properties, right? That's the only thing you could try. So,
so just in terms of general philosophy, the traditional Anderson model, you have some kind of a lattice, right?
yeah,
So in this, which
it's the Fourier
in
lattice.
the original thing, it would just be this is your lattice, it's the product of j going from 1 to 4 and n going from minus infinity to infinity, or
J is going from 1 to 4. No, oh, yeah. So original problem is on the TD lattice, right? And then I have B frequencies, right? And so I have mapped to this also TB. So you have lifted this problem to TD cross TB. So the lattice will be ZB plus D. So N belongs to ZB, and J belongs to ZD. So this is the space-time lattice.
okay. So j
J is so let's say you work on d-dimensional torus. The J is on the d-dimensional lattice. It's the Fourier series.
so that's the space.
That's space, and that's time. This is time. This is space, right? I did the Fourier transform.
Okay.
Yeah? So N is the time direction, and J is the space direction.
Okay.
Yeah? Okay?
So really what you want to do is, I mean, I think you should explain that you want to get, understand the structure, the geometric structure of the zero,
Yes,
or the
that's right.
near zero sets.
Yes.
Of this,
of the zero sets. Yep,
and how, what they so they don't percolate, they don't
that's right.
make
Yeah.
large
Yeah.
regions.
Yeah.
And you have to tune, you have to make sure that doesn't happen. Right?
Yes. Because of the singular nature of the perturbation theory. Okay. And now the key question becomes separated, right? Cluster, but relative to what? So this is you have to make precise.
What do you mean by separated?
Yeah, it has to be precise. Okay. Answer relative to a precise notion of connected, right? Okay, which we define below. Okay, it's crucial here. Otherwise, the size have to be controlled in a very precise way. Okay. Recall that my linear operator is T, a diagonal operator, plus a convolution operator, right? Now, P is a convolution operator, so there is a natural notion of connected, right? For example, the discrete Laplacian. So my example, I have the convolution P. I have there's a term cosine 2x, right? So you have a side, you jump two sides. This is connected, yeah. So you have a very natural notion of connected. So then we say that 2 points, x and y, so precising this lattice that I explained, momentum lattice ZV plus D, 2 points are connected if x minus y is in the support, when they differ by two sides, okay, in one direction. It's directional, it's important, okay, it depends on the direction. We want then the connected sets on the bicharacteristics C are small, right? Now, due to the nature of singular perturbation theory, the control on the size needs to be quantitatively optimal. Okay? Now, this brings us the hyperplanes and the hyperboloids. We obtain this quantitative control by making an algebraic description of the connected sets and variable reductions as follows. It's algebraic because these are algebraic surfaces, right? N dot omega 0 squared minus j squared minus 1 equals to 0. It's an algebraic object. So so by definition, if nj is on the bicharacteristics, if 2 points are connected, then these two equations have to be satisfied, where nu eta is in the support of the convolution operator. Right? This is very simple.
Wait.
Yes. Yeah.
Okay,
I haven't done a thing.
You shift
Yeah.
by new eta.
Yeah. They're both, they still, if they both, since you say that they are still both on the bicharacteristics, these two equations have to be satisfied.
Yes, so what's missing is that the prime, n prime, j prime is nj plus new eta.
Yeah, yeah, correct. Thank you. Yes. Yeah,
So
yeah.
you have 2 points on these
Yeah,
varieties and
yeah.
a vector connecting them.
That's right.
And you say that
Yeah.
the non-trivial thing is that the vector is actually integer value. New eta has to be integer value.
For this problem, it played a role. For wave, it played a role, but for Schrodinger, it does not play a role.
They don't have to be integer value.
They are integer values.
So that's an essential point that you're connecting these two.
Yeah.
Yeah, okay.
For this problem, yes. For Schrodinger, it's more general. Okay, but this, but the idea is I'm defining a notion of connected. Yeah.
Yes, yes.
Right. I mean, I'm not saying. I mean, I'm just rewriting what I just said here. Okay.
This is very underdetermined because we're in high dimensions.
Yeah. Yeah.
You can have
Precisely.
many solutions.
Precisely. This is the key point. Okay. In fact, it is easier to illustrate the idea on Schrodinger. Okay. It's the same idea. The variable reduction is much easier. That's why I'm going to explaining it on Schrodinger. So on Schrodinger, you have the same two equations, okay? But you don't have a square here, okay? So this is what saves you. And what you do is subtracting the two equations leads to a linear equation in J, right? Okay, i.e. a hyperplane, okay? Parameterized by nu eta, right? We go back. Nu eta are the parameters of the hyperplane, yeah? And therefore, these hyperplanes are parameterized by the initial linear solution, yeah? Okay. So a block, a connected set, can be described by a system of linear equations. You keep on writing this, as you say. You write 1, 2, 3 you keep on throwing equations, okay? The size of a block, the size of a connected set, is then bounded above by the size of the corresponding compatible linear systems, right? You keep on throwing equations until it no longer has a solution, yeah? Okay, now, under appropriate geometric conditions on U0, right? Why? Because these hyperplanes are parameterized by U0. Variable reductions give that the size is at most 2D, okay? Which is essentially optimal, because what are we doing here? We're solving J, actually, right? Solving J with nu eta as parameters, huh? So, well, J is a D vector, so you need D equations, right? And why 2? 2 is because you have two bicharacteristics. So this is essentially it. Okay? Now, for wave, the same reasoning leads to hyperboloids. The variable reductions are much more difficult, obviously. Okay? And there's also geometric reason, because this guy is essentially flat away from the origin. You are taking square roots.
By flat, you mean
you have the square root of j squared plus
the
1.
Gaussian curvature tends to 0.
Yes, yeah.
You have one degenerate curvature, but the others are non-degenerate.
You have the square root of j squared minus 1.
So
Yep.
You approach a cone.
Yes.
So the cone has only one degenerate principal curvature, so the others are good.
Okay,
Flat.
yep.
What does flat mean? This curvature.
Okay. Well, this is what I one vanish. Yeah,
direction.
yeah, one for that direction flat. Yes, you see this in the reduction actually. Okay, so I tried to do this for a while. Then I realized that aside from geometric conditions, for Schrodinger you only need geometric conditions. It's not enough. I was not able to do variable reductions until I realized that you should add arithmetic conditions.
What
Next slide. I tried very hard for more than a year. I said, well, it's like Schrodinger. Why don't I keep on doing it? I can't stop the system. So, okay. So what are the conditions? That's it. We impose the conditions that the integers under the square roots are distinct. Okay, that's kind of obvious, right? You have, and square free. So in the prime decomposition, a prime only occurs at most once. So that worked. Okay. So as a consequence, so you see, as a consequence of the square free conditions, there is the usual linear independence, right? The square roots. So this is your linear Diophantine condition, which is familiar, right? Everyone has seen this before. As well as the quadratic non-equality. You just do some computations. This is strict inequality. K cannot be equal to L, right? When K equals to L, you have omega K squared, so I should use another letter. That's an integer. Okay, there are still some degeneracy left. That you do variable reduction. Okay, it's under this that you are able to do variable reduction. Okay, so the linear independence familiar, it takes care of the usual small divisors, right? The Diophantine. The quadratic non-equality is new and takes care of hyperbolicity. Moreover, it doubles a small divisor lower bound. Okay, so if it's non-zero, there's a rigidity. If it's non-zero, then it's greater. There's a nice lower bound. Okay? This is a simple case of this paper by Wolfgang Schmidt. I mean, there's a general case using just square roots. So, but anyway, okay. It is worth noting that these are new types of small divisor which are geometric in origin. You see, they do not come from iteration and do not appear in nonlinear Schrodinger. Okay, more fundamentally, because the quadratic Diophantine property arises because it is nonlinear wave equation, is the second order in time. So there are two omegas coming in. The which one? This one. Yeah. So this arithmetic conditions is doing two jobs at the same time. There's this analysis consequence from it. Not only it helped my variable reduction, it also helped with the analysis afterwards.
Does this have to do with your square free condition?
Oh, this is when I square free. Oh, yeah, okay. Square free, okay, it's totally element. You have this condition, okay, and then you have this condition. So this arithmetic condition greatly reduces the points already to begin with on the bicharacteristics. And on this much smaller set, I was able to do variable reduction by imposing geometric conditions akin to Schrodinger. And once you do that, the nice thing is you also have this nice analysis consequences, which I later will need.
So isn't the first equation on this slide is precisely the square free condition, right?
This?
No, the first equation.
This one. Which one?
The slide you just had.
Which one?
There.
Yeah.
The first equation on this slide.
Yeah.
That's the square free condition, isn't it?
Is this the square free condition? I have to say. I mean, I haven't looked at detail. Is that the free? Is that
where it comes from?
No. There's a subtle because. No. You have to do something else. No. You have to do a bit more than this, because the constant C cannot depend on what J is. So there's something else you have to do before you can use it. No, you have to, here you really have to rely on integers. No, you cannot take square. No, you have to do something. I'm just stating the final result. You have to do something.
This is Schmidt's norm form equations or what?
Yeah, this. If this is not equal, but you have to do some manipulations to get it. You cannot take this. It's going to depend the square root. That's terrible. Okay, but the reason I'm stating Schmidt is because I find this more general, just square roots. Okay. So, and also interesting, the quadratic Diophantine condition we have not seen before is because so far most of the work probably has been using Hamiltonian formulation with first order equations. This is perhaps an interesting point. Okay. So maybe it's not so surprising that now second order will come in. Okay. So so I'm almost done. Once the separation achieved, you can extract parameters, right? You have cut down the degeneracy, actually. And okay, then Bourgain's non-resonant method becomes available to deal with small divisors. Okay, this is what I mean. The details, of course, you have to work on. But okay. So there is, however, a new analysis point in our application of Bourgain's method, namely for measure estimates. It is more convenient to lower regularity and work in the Lipschitz setting. Okay, this is a new point. Recall that the theorem is in C infinity Gevrey setting. Okay, we greatly reduced regularity, and it's probably essential too here. Okay, and I just want to say the Lipschitz setting in this business is natural because, yeah.
Say Bourgain's non-resonant method, do you mean the 2007 GAFA paper?
No, he has so many things. I mean the Orange Book, chapter 19. Yes. Yeah.
Which is based on matrix value cut-on.
That's right. That's what I mean. Okay. Yeah, he has so many things. But anyway, this is the Orange Book. I was going to bring it here, but the Orange Book, chapter 19, okay?
The one that nobody understands.
Yeah, but anyway, so the Lipschitz setting is natural here, the nonlinear problem, okay? The linear problem is natural here because of the extreme high degeneracy, okay? You have Weil's eigenvalue stability result, which said the eigenvalues are Lipschitz for free. Automatically Lipschitz in the self-adjoint case. And again, it's self-adjoint because you work with second order equations. This is the subtlety that I mentioned earlier. Okay? This is the nonlinear part. So Lipschitz setting natural, and we are doing measure estimate, that's enough. There's no reason to go to higher regularity. Okay? I'm actually really almost done. It should be mentioned that after the geometric step of extracting parameters, the ideas for the linear analysis is modeled after that of quasi-periodic Anderson localization of Bourgain, Goldstein, and Schlag. Okay, it's a 2001 or 2002 paper. Okay, so that has not changed, but in the nonlinear problem, there's this additional Lipschitz, which is kind of nice because the theorem I'm using comes from variational calculus. It's independent. Okay, so finally some literature. So nonlinear Schrodinger with external parameters, that just means that instead of considering a fixed equation, you consider a family of equations. Okay, you add some parameters in the problem. So that's the work of Bourgain in 1998, which is the paper which started the field. Sense, KM for higher dimensional PDE. And then it was followed by work by Elias and Cookson using the KM normal form method. So I would say Bourgain's method now I think should be seen as the Anderson localization or Lagrangian method. Okay, we stay on the base manifold. And the Elias and Cookson was able to do the KM normal form method, right? Infinite sequence of change of coordinates. Yeah, so 2010. And then, more recently, Porchesi, they also use KM method. They were able to eliminate the parameter, meaning you work with the fixed equation like what I wrote before. And also myself, I also have the work, the same result, but using Anderson localization Lagrangian method. And then, so these are the Schrodinger first order equation. Now for second order wave equation, so with the external parameters, again you look at the family equation. There's a SketchUp proof of Boga in the Orange Book, chapter 20.
So this is the one where he requires this is the one where he requires a random potential or something like that.
There's no random potential. No?
So what do you mean by external parameters?
Oh, it just means that that instead of looking at this equation, right? For example, you add a mu where this is, what do you call this? Multiplier. You add a convolution. You have a spectrally defined Laplacian, in other words.
So you change the Laplacian?
Yeah, he changed
Laplacian.
Laplacian.
It's like adding a random potential.
Yeah, it's like, something.
He's got other parameters which.
Yeah, that's what you meant. Sorry.
Avoid degeneracy problems.
That's right. That's right. You were. I'm sorry, I was not reflecting fast enough. But that's exactly it.
Yeah.
Okay. So he added some additional parameters to
take care of the degeneracies and
so he can skip right to the second step.
So your methods don't need that.
No.
That's probably one of the major points.
That's the major point.
So you have to extract.
That's right. And this is why all this algebra geometric stuff came in. So
at the beginning of your talk, you said something about resultants.
Resultants?
Do you use resultants of two polynomials?
Okay, I'll explain. Let me finish this. Okay. So in Boga, Orange Book, chapter 20, he had a SketchUp proof for. This is finally done. Again, as I stressed, is Anderson localization Lagrangian 2017. So your question was, sorry?
You had mentioned, maybe I missed.
Resultant, yeah. Actually, I did not say resultant, but yes, indeed, behind all of this, the resultant. So what you need is that a resultant matrix. Actually, not the resultant itself is bad. You want an effective resultant. And the effective resultant need to be small, right? Otherwise, might as well.
The degree
Yeah. So this is why for Schrodinger, it was not easy to do. It was like 8 pages of proof, but still it's relatively straightforward, so to speak, because you were dealing with hyperplanes. Okay, and then for wave, I think I was stuck for 2-3 years, and finally this arithmetic conditions was able to reduce.
Did you circumvent the resultants, or you use resultants?
It's effective result. I did not use directly resultant. No. I never directly use it. It's an effective resultant. I was able to reduce to a resultant in that language that I can deal with after imposing the arithmetic conditions. I wasn't able to do it. I thought it would be just like it's really not Schrodinger. So I think so coming. Okay, maybe.
So could you go back? I don't even remember where you stated the result that you have.
Oh.
You probably did, but I just don't remember. So maybe just go back and remind us what the final answer, what the final theorem is.
That's right, the final theorem. Okay.
Which you probably have somewhere earlier.
It's very early, at the very beginning. There's a theorem. So this is a kind of a simple version of the theorem. Oh, I skipped. So I just want to say that I think global solutions, what we call for energy supercritical, not.
Okay,
no.
So there's a class of global solutions which are quasi-periodic, which are quasi-periodic in time.
Yes.
But they're only they're only Gevrey, which of course is not a big deal, but do you think this Gevrey thing is a real thing, or just a technical thing? I mean, it should probably be analytic, I would guess, but.
Not so sure.
Okay.
In higher dimensions, I'm really not so sure, actually.
Yeah, could be.
And you mean small global solutions?
Yeah, small. Yeah, I said, I mean, the first step is non-perturbative, but afterwards it's
So this initial
perturbative.
step where you have to use, I
Yeah.
don't know, some square-free stuff and
Yeah.
maybe some work of Wolfgang Schmidt and all that. But does that have to be repeated at every scale?
Oh, no, that's,
It's only the initial
it's a
step.
one step, it's just one
Only the
step.
initial step.
It's in that sense, that, yeah, it's just the first step.
Okay.
And also another thing is, when you do iteration, you have to keep on moving more and more amplitude, Fourier coefficient. No, this is
So
one-time
that
business.
issue is really only
It-
at one step.
It's a one.
initial
It's
step
a
issue.
geometric step. There's no iteration. Once it's done, you fix the space frequency.
Okay,
And this is
okay.
it.
Yeah.
You see, the thing is, you need to put yourself on the right geometry.
Yeah, no, I understand. I mean,
So-
when we tried to look at, John and I tried to look at quasi-periodic many-body problems, we have at the zeroth level, which is what you're talking about.
Yeah,
here,
yeah,
basically
oh,
the zeroth
absolutely.
level
Yeah,
of resonance structure.
Yeah.
There are open problems in number theory related to the zeroth level, and here you can solve them, and they're still open as far as I know. So even at zeroth level, that's what I.
Yeah. This. I mean, I was saying is that. So this. You see this. Okay. So let me also put it back to the. It is known that there is a variational method to construct time periodic solutions, dating back from Rabinovitz,
Yeah.
and then there's a paper of Gourand, Nirenberg, and Brézis, but they are all in the periodic case.
Yeah.
Okay, and there's no variational method to construct time quasi-periodic solutions, because the critical points are very, very degenerate. So you could, in a way, see this algebraic way of having the initial step as sorting out the degeneracy, some sense. And the method is not variational, right? And particularly for the nonlinear wave equation, it's not. It's really not.
Okay, well,
So
thank you
that's
very
what I
much.
did. Yeah.